Welcome back to the EcoWell podcast. This is a show about the science of cosmetics. My name's Jen, and I'm your host. At this point, you've probably come across scary headlines of all the endocrine disruptors we're being exposed to, from beauty and beyond. But does the concern match the science? This conversation features toxicologist, pharmacologist, and endocrine disruption researcher, Dr. Chris Borgert. Through this episode, Chris maps the science from its inception in the public sphere to where we're at today and what we currently understand. Spoiler alert, no, the public panic does not match the science, and this has been extremely problematic, especially with the spread of misinformation and public hemophobia. For anyone wanting to understand the topic of endocrine disruption, this episode is a must listen. In case you missed it, a couple of weeks ago, I hosted the second annual Truth and Beauty e-Summit. The replay is now live on my website and YouTube page. Be sure to check it out. And Chris gave a 40-minute presentation on endocrine disruption there. So if you want more of this topic, be sure to tune into his presentation. Before we get to the episode, I just wanted to quickly thank all the wonderful people who've been supporting my SciComm work on Patreon. They're a big part of my motivation that's been keeping me going, so thank you so much for that continued support. If you want to support my work, and it's accessible, you can find me on Patreon at patreon.com/theecowell. Other great ways to support what I'm doing is by subscribing to the podcast on whatever platform you're listening to it, writing a review if you haven't already, and sharing. And with that, here's the episode. So I'm here with Dr. Chris Borgert. I guess my first question to you is, what is endocrine disruption and how does it work? Maybe it makes sense also before that to even define what is the endocrine system?
Okay, well, the endocrine system is a signaling and control system in the body, and it's a broad system that consists of what we might call effector organs. They're the organs that produce hormones, and hormones are substances that are produced in one tissue or organ of the body and then are transported either a very short distance or sometimes long distances through the bloodstream to other organs where they have their effect. It's a signaling and control system that allows the body to carry out very specialized and complex functions throughout the life of the organism, from the very beginning of life until the end of life.
Okay, so that's the endocrine system.
Right.
And so then when something is disrupted, endocrine disruption, what is that? I guess the name kind of implies it. And how does that work?
Well, you'd be surprised. And I apologize that I haven't listened to the podcast that Lyle has done, so we may have covered this. Some of this may be redundant, but I've been doing this since endocrine disruption was first reported back in the early 90s. And so to answer your question, if I may, I think I'd like to go back to the beginning, because the definition has been a contentious issue for the last 30 years or so. It's become more contentious recently. An endocrine disruptor was initially defined by the people who were its strongest advocates. In other words, the theory that chemicals in our environment were disrupting our endocrine system. They defined that, and it became codified at a conference called the Weybridge Conference. It was held in Weybridge, England. And that definition said that an endocrine disruptor, and I'm paraphrasing, I could pull up the document and quote you exactly, but this is pretty close. The Weybridge Conference concluded with a publication that said an endocrine disruptor is a chemical that causes adverse effects secondary to altering the endocrine system. And that definition was generally accepted by the people who were arguing that endocrine disruption was a newly discovered mode of toxicity that we needed to be very concerned about. It was eventually also adopted, and in a slightly different form, by the World Health Organization and the International Program on Chemical Safety, IPCS, so WHO and IPCS. Around 2002, they clarified some potential ambiguity in that definition. They clarified secondary. That definition said causes adverse effects secondary to an alteration of endocrine function. This definition said that an endocrine disruptor is a chemical that has an endocrine mode of action and consequently causes adverse effects. So they just turned the phrase around and they made sure that that phrase secondary to was clarified as and consequently causes. There's really not much daylight between those definitions. Those are pretty consistent. So we have essentially three aspects. An endocrine disruptor is a chemical that causes an adverse effect, and it does it through an endocrine mechanism. So we have to think about, well, what is an endocrine mechanism? And an endocrine mechanism is a mechanism that operates through the machinery of the endocrine system. I described that, what the endocrine system was. So it's a chemical that either mimics a hormone or blocks a hormone. The endocrine system basically has two broad components. There are the endocrine organs that produce hormones, and then there are the organs that are sensitive to hormones. And those organs and tissues are composed of cells. At least one of the types of cells in that organ and tissue will have receptors for particular hormones. We can think of this as it's often been described in pharmacology as a lock and a key mechanism. So you can think of the hormone as the key and the receptor as the lock, and there has to be a very precise fit between the key and the lock for that key to open the lock. So an endocrine disruptor would be a chemical that interferes with those processes in some way sufficiently, and this is my addition, sufficiently strongly to produce an endocrine-mediated adverse effect. So people can quibble about what's adverse and what's bad, but those components are important, that the chemical works through an endocrine mechanism, and it's broader than just the synthesis of the hormone and the receptor, because the receptor, you can think of that as there's an opening to that lock that is very specific for a key with the exact shape. But then once you turn that key, there are tumblers that actually unlock the door, and there's a bolt that goes into the door frame. So all of those are second, we may call them in some systems, they're called second messenger systems. In the endocrine system, it works a little differently, but there are events that occur after the receptor that mediate the cellular response. And so those would be parts of the endocrine system as well. And then there's the organs that metabolize hormones and so break them down. So we're constantly synthesizing new hormone and breaking down existing hormone, and the body balances those levels precisely. So there are a number of opportunities to interfere with the endocrine system and its function, but I think the purpose of that definition was that it needs to be the mechanism or mode of action needs to be specific to the endocrine system. So again, we have these three components. It has to work through that endocrine mechanism. It has to produce an adverse effect, and there has to be a causal relationship between those two. And I can give you a quick example where there can be some disagreement. Ethyl alcohol, the alcohol that is in adult beverages, when consumed in high enough quantities and frequently enough, can alter liver function. And of course, the liver is an organ that is involved in the metabolism of hormones. So if you cause significant liver toxicity, you can then disrupt the levels of hormones or alter the level of hormones in the body through that mechanism. I would not call that endocrine disruption because ethyl alcohol is not specifically interacting with any of the machinery of the endocrine system. It's toxic to the liver. So that's a liver toxicity mechanism, not an endocrine mechanism. But if you use a different definition, such as a definition that is preferred by the Endocrine Society, for example, they have defined an endocrine disruptor very broadly as a chemical that alters any aspect of hormone function, is one way they phrased it. I should point out that the IPCS and Weybridge definitions, both in those publications, made clear that that endocrine disruption was something that could only be ascertained in an intact organism because of the control properties of the endocrine system. It's one of the major control systems in the body. So it's going to be very difficult, if not impossible, to assess that in vitro assays, in tissue culture systems, or some other system that is simply a few components out of the body, or in a cell system, in a cell-based experimental system. But the Endocrine Society definition doesn't place that restriction. It's not as focused. It's much more broad. So it opens it up to classifying something like ethyl alcohol up potentially as an endocrine disruptor. So it's much broader. But I think the generally accepted definition around the world by regulatory agencies and most who deal in this area, and even the Endocrine Society has stated that they'll use that definition when they have to, but they prefer a different definition. So that's why it's a complex issue, is because even the definition has been somewhat debated. And then we could go into other layers. I won't, for the sake of time, I won't try to go into all of it, but you can then break down each of those components of the IPCS, World Health Organization definition, and you can say, well, what's required to determine that a particular effect is adverse? And another question arises. Many have objected, including the members of the Endocrine Society, for instance, would object that requiring a causal relationship to be established between the endocrine mode of action or the endocrine mechanism and the adverse effect is too high a bar. So we can't really do that. Some would reject the definition altogether, and others, such as ECHA, which is basically the European counterpart to the US EPA, some parts of the FDA. So the regulatory body in Europe would say that there's a biologically plausible causal relationship. It somewhat reduces the hurdle for satisfying the definition, and then the question becomes, well, what's biologically plausible? So you can see it's not a clean, straightforward question to answer, but I think that the IPCS WHO definition makes the most sense. And I think that's what people think of when they think of endocrine disruption. They certainly think of something that causes adversity, not just something that causes a change that you can measure.
Okay, so you said a lot of really interesting things that I think we should probably lean in on. You talked about, I forget how you phrased it, but I'm thinking about this in the context of cosmetics, and I think could kind of tease out what I'm trying to get at. There's a lot of ingredients in cosmetics that are purportedly estrogenic. This is an example that Lyle gave when he was on my podcast, and I think you guys may have published something on this specifically. So yeah, please expand. In vitro, you may be able to show that X chemical has an estrogenic impact because it causes this effect. But when estradiol is in that environment, then it isn't, you said sufficiently strong. That's what you said.
Yes.
It isn't sufficiently strong to outcompete estradiol in the estrogen receptor to have that impact. And so it either has to have the sufficient specificity to outcompete, or the concentration has to be strong enough to have that outcompeting action in reality. But the issue is, if estradiol, which is in humans, isn't in that environment, then you may artificially inflate the outlook of endocrine disruption. Okay, I'll stop talking. That was really messy. I eventually got there of like trying to make sense of what was going on in my head.
I'm giving long and complex answers, and that makes it very difficult to frame a cogent follow-up immediately. So you did well. You did well. That I said sufficiently. It needed to act through that endocrine mode of action or mechanism with sufficient strength to actually cause any type of physiological response, let alone an adverse response. So this is actually something, and I don't know if I'm going into too much detail, simply stop me. But this is something that I've been saying for more than 25 years. I served on the US EPA's Endocrine Disruptor Screening and Testing Advisory Committee. I basically characterize my career as trying to bring pharmacological concepts and principles into greater focus in the realm of toxicology, because those principles are well established and they underlie all of these questions. So when I was serving on the EDSTAC, this was a large federal advisory committee. It met routinely about every other month for a couple of years in various cities around the country, and it had members from every potential stakeholder and viewpoint that you could imagine. But one of the things that came up were these in vitro assays, and that committee actually designed the screening and testing program that the US EPA has used ever since. So the committee was active from 1996 to 1998. One of the things that came up was exactly this question. Any statistically significant result is not necessarily a biologically significant result. And we know that from pharmacology, from decades and decades of pharmacology. We know very, very weak interactions, for example, with the estrogen receptor are not meaningful. As early as 1997 or 1998, I was raising my hand in those meetings and saying you can't simply make the interpretation based on a statistically significant result, especially considering the fact that when we do those in vitro assays, so we've got a tissue culture full of cells that have estrogen receptors. But one of the things that we've done for decades is we eliminate serum from the culture. We eliminate any chemical that, including serum, which is all of our cells are, serum is the main component of blood. So all of our cells are bathed in serum. But in order to make these cell cultures, these in vitro experiments, very, very sensitive, we learn to grow them in the absence of serum so that we can detect very, very tiny changes. And that's fine if what you're trying to do is understand, for example, how in drug development, how changing a molecule slightly might affect its estrogenic activity. That's a very useful assay. But you can't directly interpret any signal, any estrogenic signal, as if it's necessarily physiologically meaningful. So you can use those assays, but only if you understand how strong an estrogenic response is actually needed to be physiologically relevant. And that was stripped out of the process. The argument was that we can't take a chance that we would miss anything, any chemical that might be an endocrine disruptor. So in the screening phase, we're going to assume that any statistically significant increase we can see in those in vitro assays is a positive result. Turn this around, if your purpose were to search for chemicals that might actually affect the endocrine system, you'd have to set a threshold. You'd have to figure out what response is too weak to bother with and what responses are strong enough to actually produce a physiological effect. And I've been working on that ever since. And I teamed up recently in the last few years with Lyle, and we published the most recent publication on that topic, showed that you have to have a certain level of receptor occupancy in the body. In other words, in the context of the serum and all the chemicals, including estradiol is not the only one. There's estradiol, there's estrone, there's estriol, there's androstenediol, there's DHEA. Many people are familiar with DHEA. It's a common dietary supplement. All those chemicals are naturally in our body. Our body produces them. We have to have them for life. And they're all interacting with the estrogen receptor. So it's not just estradiol. Estradiol is the only one that's really strong enough to send powerful estrogenic signals. Maybe androstenediol, maybe estrone and estriol, but the big player is 17-beta estradiol. So you have the estrogen receptors that are almost 100% occupied. So in other words, like this is lock and a key. There's a key, in every lock in your body. So another key has to come along and be strong enough to push one of those natural keys out and take its place. And there are very few chemicals that are strong enough to do that. They don't have enough what we call affinity. They don't have a tight enough fit in the lock to actually displace one of those endogenous molecules. And so that's the reason that we have these thresholds. A previous paper that I published with a couple of other pharmacologists a few years before the paper that Lyle and I, and John Matthews, who was on the previous paper now that I'm talking about, he was also on that paper. We showed that clinically there is a threshold for that, we call it potency, for the estrogenic potency of a chemical. So we went through a lot of clinical data and showed that practically there is a threshold. So the paper that Lyle was referring to is a paper where we went back and asked the question, if there is truly this clinically identifiable threshold, there ought to be a physiological explanation for why that threshold exists. And so that's what that paper did. And I think it was a fairly convincing demonstration of why these thresholds exist. The way we tested the hypothesis, we could have come up with an answer that refuted our original claim, but in fact it didn't. And I've been told it's not published yet, but there's another group of researchers who recently tried to replicate our method. They used data that could have falsified our method, that could have punched a hole in it, but instead their analysis corroborates ours. If anything, it shows that we were conservative in the way we set our threshold. In other words, we didn't set it too high by any means. We conceivably, the threshold could be even higher than we showed. So it's very consistent with our results. So that's what we mean by sufficiently strong. If the chemical is not a potent enough estrogen or is not a potent enough anti-androgen, we may be able to show in some in vitro assay and sometimes in an in vivo assay, sometimes in a particular rat model. The eutotrophic assay is a favorite. But again, we've modified the system there. We usually take out the ovaries or we time the administration in a rat at a specific point. It's just within a day or two. You have to get it exactly right. And then we overwhelm the animal with the chemical, and we might be able to observe an increase in the weight of the uterus. But we've gamed the assay to make it particularly sensitive. And that doesn't mean that the chemical will necessarily have any effect in humans. Sorry, I'm going on, but another thing that comes up in this is, are rats a good model? That's what we usually use. Are rats just little people? And it turns out they're not. They actually operate on hundreds of fold lower concentrations of, for example, 17-beta estradiol than do humans. So that makes that background that I talked about of endogenous chemicals that are occupying the estrogen receptors, that makes them a little more susceptible to a very large dose of some chemical that we're asking whether it's an endocrine disruptor. So it's an important thing to keep in mind. But as I say, in the discussions that you will see, even in the scientific literature, that aspect is usually ignored.
And so to give, I guess, a case example of a group of chemicals that people are commonly concerned about that are relevant to cosmetics, parabens, or at least the parabens that are approved for use in cosmetics. So I believe butyl paraben is around 10,000 times less estrogenic than estradiol. Is it reasonably going to be able to outcompete at the estrogen receptor? And then, okay, so then regulators are starting to, or NGOs or whoever are starting to talk about different parabens being estrogenic. At what dose? So how much of this would you need to actually have that impact? For context, parabens, the approved use rate is, depending on the paraben, like 0.3% in the finished formula. Is that reasonably going to have endocrine disrupting impact in light of the potency, in light of the concentration?
No. In the paper we published in 2018, I published it with Steve Baker and John Matthews. I created a scale to make this very obvious and to put various one to put the various chemicals at issue on the scale. We use the estrogen receptor model as the example. So at one end of the scale, the potent end is estradiol and the pharmaceutical estrogens. And at the low end are things like the androgens. This is an interesting point. Testosterone will stimulate the estrogen receptor in these assays. And so will, now people could have challenged. They'll say, well, that's because in these cell systems, testosterone can be converted to estradiol. Testosterone is only one synthetic step away from estradiol. So maybe these cells are just converting the testosterone to estradiol, but other anabolic steroids that can't be converted to estrogen have the same potency. So those have 10 to the minus fifth to 10 to the minus sixth, the relative potency of 17 beta estradiol, which we use as the reference chemical. So that's one. So you're referring to the parabens that are 10 to the minus 4. That would be 10,000 times less potent. We initially said the threshold was at least 10,000 times lower and is likely to be higher by at least tenfold. And the parabens are below that threshold. They're no more than a 10,000th. That is clearly below the potency that could ever manifest an effect. I wouldn't claim that means parabens can have no effect at any dose, but they're not acting through an estrogenic mechanism when they cause that adverse effect. You're basically testing the chemical at such a high dose that it's producing an effect, but it's going to be by some other mechanism. That potency threshold tells us that it's not going to operate through that mechanism. There may be some other toxicity that's being caused or some other mechanism, but at low doses, it's not going to cause any effect through the endocrine system. And that's what you see. What most people don't have the background to understand how we actually test chemicals. And we test chemicals at hundreds, at least hundreds, usually thousands or 10,000 times higher than the dose that humans can be exposed to. So you may see an effect, but it may have no applicability to the doses humans actually receive. And it may have no applicability to these endocrine mechanisms. So as I say, the short answer is no. I believe it was butylparaben that's even in the 2024 paper, we put that chemical on the scale because some data had come out on the potency of butylparaben, so we put it on our scale, and it's clearly below the threshold region. So are a variety of other chemicals. The silicones is another. There's cyclic siloxanes that are in cosmetics and a number of. They're usually the polymers, so you're not even exposed to the single chemical. It's a polymer, but that's another good example of chemicals that simply have insufficient potency to ever manifest any kind of estrogenic effect. But if you give a rat whopping doses of the chemical, you'll eventually reach a concentration that's high enough to do something adverse. That's required. That's the way the tests are done.
Now, something in response, I'm sure somebody listening to this is thinking about this question. I get it a lot on my social media. People are concerned about a quote unquote cocktail effect. One chemical is fine, but the sum of the chemicals we're exposed to, that's where we run into issues, whether it's like a mixture of different chemicals or that single chemical. It doesn't even really make sense when I'm like saying it aloud with like people are concerned about, well, parabens might be in like multiple products. So it's demonstrated to be fine with the exposure relevant to that single product. But what about if it's in all these different products? Except like on the other side of it, the cosmetics industry is like avoiding that ingredient now because of consumer fear. So, I mean, there's that. And then also like aggregate exposure factoring in risk assessment. So I guess what would you say to people who are concerned about a cocktail effect from chemicals leading to endocrine disruption?
Yeah, it's a good question, and it comes up all the time. In fact, that's another area that I focused on long ago. I published my first paper on mixtures in 2001. because that issue came up in the late 90s in terms of potential for endocrine disruptive effects. I think we can use that last example that we talked about, the papers that I've published on the estrogenic mode of action and what kind of a threshold it takes. I think we can use that as an example. At the risk of being a little silly, I'm going to use an analogy. All right, so the answer is that no, the mixture effect is not a relevant effect unless you're dealing with the mixture effect is slightly different than the aggregate exposure concept. So let's take the aggregate exposure concept. If you're talking about a particular chemical, this has been an issue with some pesticides, and it's most well worked out in the realm of pesticides. You may have the active ingredient of a pesticide appearing in a number of different products. That particular active ingredient or active ingredients that have an almost, maybe a different chemical, but almost identical mode of action. And remember, all of those active ingredients are capable of acting and causing an effect by that mode of action. You may be exposed in lawn products. You might be exposed slightly through the diet. You might be exposed in various ways. And if you add up those exposures, that might give you a better estimate of the overall risk than if you do it one at a time. But remember, the salient feature is each of those chemicals at a sufficient dose can work through basically the same mechanism and cause an adverse effect. So therefore, you're adding like things together, and that makes some sense. But let's go back to this example of occupying the estrogen receptor. If the chemical alone is not potent enough to overcome all of those endogenous chemicals that are in our system, the idea that many, many weak chemicals will eventually have an effect can only be demonstrated, first of all, at extremely high doses. And it's a theoretical demonstration. So theoretically, you could get to a high enough dose if you're just doing these receptor occupancy calculations. But again, what comes into this is these other mechanisms. In order to do anything theoretically, you would have to have such high doses of the chemicals. They would be producing some other toxicity. You're simply, at some extremely high dose, you simply make the animal sick. And these would be doses that are thousands, if not hundreds of thousands of times higher than anyone could be exposed to. So it's a theoretical exercise that doesn't have a basis in reality. Now, here's my silly example. People sort of paint endocrine disruption as, let's think of a game of musical chairs. So there are 10 chairs in a classroom. Children can play these games of musical chairs, and you can say, well, the more children that come into the classroom, the more those chairs are going to be occupied. Well, as long as you've got a lot more than 10 kids in the classroom, those chairs are going to be occupied anyway. So you can keep piling in more kids, and it doesn't necessarily mean that the chairs are going to be more occupied. But now let's introduce 17 beta estradiol into the classroom. This is the front line of the Philadelphia Eagles. They come into play. They're bigger. In other words, they're more potent. They're bigger. They're stronger. As long as there's 10 of them, let me tell you, they always get a seat. They always get a seat. It just doesn't matter how many children you put into the classroom. They're not big and strong enough to displace those linemen. It's theoretically an issue, but practically it just doesn't make sense. And then if we were to do, as I mentioned, I hope I mentioned it already. Maybe I haven't. This is another problem with science, especially with the field of endocrine disruption, is an important aspect of scientific research is called falsification. In other words, this comes from the philosophy of Karl Popper. And Popper says, we never really prove anything directly. We can only fail to disprove it. The way scientific facts become facts is we try to poke holes in a theory or a hypothesis, and when we can't do it, from any different angle that we approach it, it starts to have credibility. But there's no incentive for doing that in modern science. In fact, the new director of the National Institutes of Health, Jay Bhattacharya, has said exactly that, and he intends to change it. He says the incentive structure is wrong. We only reward new discoveries. And so it doesn't reward, if there's a publication that comes out making a claim, there's no reward for a different scientist to try to falsify that. It's not a new discovery. Everyone's trying to publish something new and interesting and exciting. So we have a distorted incentive system. But if you take that mixture theory and you apply it broadly, you would come to the conclusion that because there are so many chemicals in our foods, not only in our own system, but in our foods, in our environment, and some of those are natural compounds. In fact, some of the most potent are the natural, what's called the botanical estrogens or the phytoestrogens. And we evaluated those in all of our recent papers. Those turn out to be stronger than more potent than many of the so-called environmental endocrine disruptors. If we would add all those together, you would come to the conclusion that we couldn't possibly be alive because the mixture would have overwhelmed the endocrine system of every person alive, because we're just exposed to so many. If you start to add in all the chemicals, then the theory breaks down. And you see that the theory doesn't really provide a good explanation for these alleged effects, for the alleged cocktail effect. So if that's operative, then you always have to ask, well, if that theory is true, what else must also be true? And so it must also be true somehow that when you add everything together, it's somehow safe, and you wouldn't reach that conclusion. So we can falsify that theory by, in this case, by a simple thought experiment. And our recent paper, I think, demonstrates that. So it's not something that I worry about, because it's common sense, I think, would tell us that that's not going to cause health effects when the individual chemicals themselves are too weak to do anything.
It strikes me that some of the discrepancies here are due to conflating hazard with risk. This will lead really well to my next question. And just as easy explanation for this concept for anyone who maybe hasn't listened to my podcast before, a potential hazard for water, something we need to survive. There's lots of healthy attributes to water. Obviously, I'll die if I don't stay hydrated, is water poisoning. If I drink, I think it's around 30 glasses in one sitting, obvious variation depending on the person, I can get water poisoning. However, if I drink one single glass of water, how realistic is that hazard to come to fruition? So the exposure will dictate the potential end impact. So one glass of water is not only safe, it's healthy. So there's this whole hazard versus risk versus benefit equation to kind of put some of these topics into context. Same when we're talking about this topic, it appears. Now, a lot of people will talk about non-monotonic doses when it comes to endocrine disruption. What's going on there? And the reason why I brought this up specifically is I think it was 2020 or 2021, I was put on a debate by Beauty Independent. It was me and a cosmetic chemist from Rutgers University, Ricardo Diaz. We were Dirty Beauty, and we were up against these two marketing people who had no science background. The one person who talked the most was Lindsay Dowell from Beauty Counter. And she made the statement, this person who has no science background made the statement that modern toxicology was wrong about everything because sometimes dose doesn't make the poison. And endocrine disruptors were an example of that. So, what would you say to that? And then also, what's just generally going on with this idea of non monotonic doses as they apply to quote unquote endocrine disruptors?
I would like to give a very short answer, but I'm afraid I can't give a very short answer. I'll try to at least give a clear answer. When a new scientific theory is proposed to explain something new, in other words, the idea that very low levels of chemicals can be a problem even when higher levels of chemicals aren't. So the idea is that dose response may go up, but it may come back down, and we're testing at too high doses to see that. There are a number of issues there, but in general, what has been reported to be non-monotonic responses are simply responses that are in a particular experiment may be statistically significant, but they're not biologically relevant. And so there, in other words, there's a very tenuous speculation that this up and down, say in the response of the estrogen receptor, is actually responsible for some purported adverse effect, because the up and down is really within either the normal range of the organism, usually rats that are being tested, or some other, or sometimes it's in vitro. It's within the range of variability. It's not a biologically relevant response, is usually what we find. But there's another problem, another complication, and you just put your finger on it with water. What if you drink a thimbleful of water every day? Only a thimbleful. You're going to soon have health problems. And so we could say there's a non-monotonic dose response curve for water, because you're going to have adverse effects when there's too little, and you're going to have adverse effects when there's too much. And interestingly, with the endocrine system, sometimes, there's an optimal level of hormones in your body. You need enough, and our bodies try to regulate that within appropriate levels. And the body has a phenomenal system for doing that. It's brilliant. And so we're able to maintain the right level of hormones, unless you have an endocrine disease. I mean, there are certainly points where you can't. But your body does a remarkable job of doing that. But like water, there are deficiency effects. If you have too little hormone, there will be adverse effects, usually on the organs that are responsive to hormones, because they're not getting enough hormone. You can also have responses when you have too much hormone. And again, those often are observed in the organs and tissues that are sensitive to the hormone. And sometimes it's difficult to tease out, not always, but are we seeing a deficiency effect? Are we seeing an overdose effect? So that's a non-monotonic response. I mean, that's to be expected based on what we know about the endocrine system. So there are a lot of factors that can give us non-monotonic responses. Some of them are meaningful, like the deficiency versus overdose response. Some of them are not particularly biologically meaningful, and those tend not to be very reproducible. I'm not rejecting the concept out of hand, because certainly we know about deficiency effects and they apply to more things than hormones. But I do reject the idea that this is occurring with abandon because of all the chemicals that we're exposed to. I think that's probably not occurring in a way that's biologically meaningful. Pointed out the problem with potency. Well, you're really not going to have any up and down, because your body, the natural chemicals in your body, are already occupying all those receptors and all those enzymes that metabolize hormones, etc. They already have their hands full with the chemicals your own body makes. These other weak chemicals are not going to make much difference. But I have to say one more thing, if I may, about, and it goes back to this concept of a new theory, and falsification. When a new theory to explain, so in this instance, to explain this idea that these weak chemicals are acting at low doses because they have these non-monotonic effects, a new theory has to explain not only the new proposition, it also has to explain what we already know. And when we don't have an incentive in our research programs to actually try to poke holes in this, we never attempt it. If you think about this, from the standpoint of, if that's true, what must also be true? The theory breaks down rapidly. It just doesn't, it actually doesn't hold water. You have to ignore all of the chemicals that could interact with some component of the endocrine system very weakly, that we're exposed to naturally, natural components of food, not contaminants, natural components of food, natural components of our environment. It would apply to them too. And when you try to account for everything, the theory doesn't hold up. It doesn't make sense. That's what I have to say about the non-monotonic dose responses. I'm not throwing it out altogether because of the overdose and deficiency aspect. That's real. That's real with vitamins, real with a lot of things. I don't think it's at play with endocrine disruptors.
So if you watch the news or open up the internet, you may have seen headlines around toxic chemicals causing a fertility crisis. There were headlines post Shauna Swan wrote a book called, I think it was The Egg. I think that's what the book was called, where she made the statement that we're heading towards like the extinction of the human race by the chemicals that we're exposed to, specifically with respect to endocrine disruptors. She talked a lot about phthalates specifically. Are toxic chemicals causing a fertility crisis? Why or why not? And I'll tack on the question, why is this narrative so popular? And like, honestly, it's something, this is maybe an unpopular opinion regarding how this has been framed, but I feel like there's a lot of like transphobia that are underpinning some of the popularity with, we don't want males to be more feminine kind of thing. We also like care deeply about women having more babies. Like that just seems like some like very, okay, unpopular opinion. I may have to edit it out, but like some like traditional values that are like maybe getting more popular, that are maybe like fueling some of these narratives on the interwebs. Unpopular opinion. I'll stop talking.
Well, I'm not a psychologist or a sociologist, so some of that I can't get into, but at least not as an expert. So the first thing I would say about that theory is that it's not a new theory. This has been around since endocrine disruption made a splash. In fact, one of the co-authors on Theo Colborn's book, Our Stolen Future, and it was Theo Colborn and Pete Myers, and I apologize if I botch her name. It's I believe her name was Diane Dumanodsky, but I may have mispronounced that, and I apologize to her. So the story is that she had to walk back a few of her recent theories at that time, and this is back in the 90s, because she had said we had a population crisis in the other direction. You know, that the Earth was becoming too populated, and of course, that was a theory that we were on the precipice. We were approaching the edge of the cliff back in the 90s, and that chemicals were going to plummet the human population to unsustainable low levels because of these fertility and reproductive problems. At first, it was reproductive toxicity, but it was the big concern. So remember, this was early 90s. Well, that didn't happen. The theory continues to be refueled and retooled by new claims about chemicals, but it doesn't seem to be playing out in an enormous population decline. Now, I understand that there are areas of the world where people are not at replacement reproductive rates, and so migration is filling holes in society. I understand all that. The thing is, you have to take very seriously that what you see on the population level doesn't necessarily apply to an individual couple. So there are certainly individual couples, and maybe that is on the rise. Maybe there's a higher incidence of couples having a difficult time having children, but on a population basis, we can see that that's not really playing out. So that doesn't dismiss it for the individual couple. It's still a problem. But on the population level, I don't buy it. That theory's been around for a long time. Shauna Swan has also, I don't know, it was 15 years ago or so, published a paper that the birth ratios between males to females was changing. But again, do we even take into consideration all the possible explanations for that? And historically, we have data to show that this isn't necessarily true for any individual couple, but as couples age, they tend to have more girls than boys. Why that is, I'm not sure we know, but that is the trend. So, are couples waiting longer to have children now than they did back in the 40s and 50s? Undeniably. So, there are a number of factors that can play into that. So, a lot of these theories have been around a while. Some have made a big splash and died away, but they never seem to be corrected. So I don't think that you can attribute, a population decline or fertility problems directly to these chemicals. These are complex questions that have a lot to do with societal factors. I'm told that's not my area of expertise. So there are a lot of factors involved, probably nutrition, lifestyle, our societal behaviors, et cetera. And there's just not I haven't seen a convincing explanation of how endocrine disruptive chemicals or just chemicals altogether work together to produce this. Although, you can certainly show that at some level, when organisms are exposed to overwhelming amounts of chemicals, it makes the animal sick. So you have those two things. I'm not sure you can actually connect the dots and put them together. One of the things that made me smile, though, is you mentioned the men are not as masculine and the history. It was around 1996. The researcher has passed away, but a particular researcher from the University of Florida was invited to testify before Congress, and he told Congress that they were half the men that their grandfathers were because of endocrine disruption. That was brilliant because he knew how to get their attention. That made them all worry, and it made them all more interested in funding endocrine disruptive research, which is often a driver. It goes back to the incentive structure. If you want to get grants and you want to be funded and you want to continue to publish your papers, you've got to find something that grabs attention, and it's got to be something kind of new. These things have been around for a long time. I don't think panned out into a population crisis.
I also wanted to just comment on there's so many confounding variables that you've brought up. People are having kids later, which may impact success for having kids that maybe people should be thinking about. But also, like, people are also choosing not to have kids when there is greater equality for males to females in a population. Typically, there are lower reproductive rates. A lot of this just doesn't make sense, and it comes back to some of these like kind of deeply conservative ideologies that maybe underpin the traction of some of these ideas that I feel like are so easy to poke holes into, but people aren't for some reason. On the topic of Shauna Swan, Lyle did a response episode to Shauna, was on the Huberman podcast. I think it was 2 years ago at this point. And so we went through 40 minutes of the podcast, which took us quite a long time to get through, and dug into some of the things that she was saying. So if you want more on Shauna Swan specifically, go listen to that episode. But then a comment that I got on that episode from somebody who shall not be named, the comment was, "You actually do need to be concerned with toxic chemicals and phthalates in our beauty products. It's disrupting our organs, cells, and everything in our bodies. Why do you think there are more instances of cancer these days? It's a no-brainer." I feel like the conceptions around cancer rates also are kind of confusing to the general public, and I don't know if you can comment on that. So I guess, what would you say to this person who's commented that there's so much more cancer these days, and that's due to toxic chemicals that we're being exposed to?
Well, it's a theory, but every theory has to be supported by data. Let's go back to the start of this. One of the first questions you ask is, what is an endocrine disruptor? It's a chemical that causes an adverse effect as a consequence of an endocrine mode of action, or has an endocrine mode of action and as a consequence causes. It's that causal question. How do you know that it's phthalates that are causing this? How do you know that you don't know that? And here's another thing that has amazed me. I've been in this longer than I ever thought the issue would. I thought this would go away a long time ago, because the question is reproductive problems, et cetera, et cetera. We already test for those, whether the reproductive problem arises from endocrine disruption or some other toxicity. The real issue is, does a chemical cause reproductive problems? Does it cause cancer, et cetera, et cetera? But linking this mechanism to the outcome is really important. How do you know it's the phthalates that are causing it? How do you know it's endocrine disruptors? How do you know it's chemicals? How do you know it's not something else? It's one thing to propose it, and it's another thing to actually show that that is the cause, or that it's a significant causal factor. There may be a number of causal factors, but the short answer to this is cancer is a disease of aging. We've known that for a long, long time. And we know the reasons for that. As we age, our systems wear out, especially things like DNA repair. Antioxidative processes in the body decline. Our hormone levels decline. A lot of things start to be less robust the older we get. We become more susceptible to these, in the case of cancer, this normal rate. Your physiology isn't perfect, and little mistakes are constantly made in DNA reproduction. And some of those lead to mutations that can become cancers. Normally, we have DNA repair, we have things like glutathione and other antioxidants that reduce that. We have the immune system that attacks and eradicates some of those aberrant cells that are on their way to become cancer. But as we get older, all of those protections start to break down. So the older our population becomes, the better job we do at prolonging our lives, cancer rates go up. Now, the other side of it is people will say, well, we're seeing more childhood cancers. We are, I think. The data I've seen, there are certain types, at least, of childhood cancers that seem to be on the rise. But there's another factor. Our infant mortality rates are far lower than they ever were. More infants survive today, and that's a wonderful thing. It's still a problem when they don't. We're still working on that. We'd like to have that to be 100%, but that means that infants that may have not have survived previously in decades past, who had some sort of genetic weakness or some sort of metabolic imperfection, they're now surviving. And that may underlie the cancers. I can't say that we've completely disproved that theory, but again, we have to explain all of the data, and we have to look at all of the possible contributors to decide if that's really the cause. And so it's easy to make those statements. You can believe that. I don't begrudge anyone their beliefs. But my first job as a scientist is to be skeptical. And the hardest thing to do is to be skeptical of your own ideas. But that's what our obligation is, try to poke holes in the things that we think are right. So I see those kinds of responses like you do. The only thing I can say is, well, let's walk through the data. Let's see if that theory is really supportable when we consider, all the possibilities. And I think that's unlikely. That doesn't mean there's not a constellation of effects from lifestyle, chemicals in our diet, that all together could be causing us problems. But I think simply to say that it's the amounts and the types of chemicals we're exposed to is an insufficient explanation.
How many environmental chemicals are known to disrupt the endocrine system of humans?
1.
Is it birth control?
No. But that's, if you think, and I answered it with one word answer. You said how many, so I gave you an answer. Now, obviously, that depends on how we look at it. But yes, birth control could be viewed as endocrine disruption, I mean, that's exactly what the mechanism is. You're preventing pregnancy by altering the normal function of the endocrine system. And I've seen debates on this topic that actually are at issue in litigation cases, where people make the argument that whether it's an endocrine disruptor or not depends upon the intent of the person prescribing the medication. But think about that. That's not a very scientifically satisfying definition. I have to know what you intended first before I can define the chemical scientifically. So, in other words, if you took the birth control by accident, it's an endocrine disruptor. And if you were taking the birth control for the purpose, birth control pills are actually taken for a number of reasons other than just prevention of pregnancy, but you could certainly say that's endocrine disruptive. There are many other types of drugs that are intentionally endocrine disruptive. Treatments for hormonally related cancers are disrupting the endocrine system. They're anti-estrogens for breast cancer, for various types of estrogen related or estrogen sensitive cancers. But the one I had in mind was actually, there's no question about this one, that we know the mechanism, we know what happened, we know there's a causal relationship between the mechanism and the clearly adverse effect is diethylstilbestrol. It's a very potent estrogen, and it was given in the 50s and 60s, was actually eventually banned in the 70s. It was given for prevention of miscarriage. And it's an interesting one. It was given for the prevention of miscarriage to actually millions of women. But there was never a clinical trial conducted on DES to show that it was efficacious. In fact, it wasn't. It turns out it didn't prevent miscarriage. But because there was not a clinical trial or a series of clinical trials conducted to discover the optimum dose and the safe dose for preventing miscarriage, there was a great variance in the dosages that were given among the different clinical centers that were using DES to prevent miscarriage. And all these years later, we know that it was only the clinics that were giving the highest doses, which were 12 to 14-fold higher than the other clinics. Those were clinics in the United Kingdom. And these are not small numbers. We have follow-up on thousands and thousands of DES daughters and sons. In other words, the children born to mothers who took DES and it was given during the first trimester of pregnancy. So we have follow-up data and all of the adverse effects. It occurred in both males and females. It was in the reproductive tract. The one that everyone knows about is the effect on, it was a relatively small fraction of the DES daughters, but a serious and tragic adverse effect. They developed uterine adenocarcinoma when they got to reproductive age. And so it's just, it makes you emotional to think about that. That's a horrible adverse effect. And it's a serious one. So that one is still used as the sort of the poster child by the advocates for the endocrine disruptor theory, but they always ignore the part that I just pointed out, is that it was only in the high dose clinics. There was a threshold. Even for that potent estrogen, you had to have enough, and lower doses didn't produce those adverse effects. So there was a threshold. I've published on it, and there's a paper in 2012 where I first coined this term that Lyle probably mentioned, that we just published the most recent paper on the human relevant potency threshold. I used that as an example, and I went back and dug through the data for rats treated with DES and showed that our usual assumption that the test species are much less sensitive than humans. So we always adjust. If a certain dose is safe in these laboratory rats, we assume humans would be sensitive to even lower doses. But it's actually the opposite for DES. The rats are far more sensitive than humans. Some of these concepts that have woven into the discussion of endocrine disruptors were debunked in the data that we've had for decades. And another one, if I can throw it in quickly, the Endocrine Society, for example, in a 2014 paper, they claim that research showed they didn't use the word inconceivable. They use the word incontrovertible proof that there are no thresholds. They claim that this comes from a series of studies done in reptilian eggs, where they paint chemicals on the surface of the egg. And what's interesting about these, a couple species of reptiles, alligators and red-eared slider turtles, sex determination is controlled by the environmental temperature in those species. So you can take eggs out of the nest in the springtime from red-eared slider turtles or alligators, and if you put them in the laboratory in an incubator at a constant temperature, it's actually reversed for the two species, but in one species, a temperature of something like 35 will give you all males, and 37 will give you all females. So what they do is they paint these eggs with chemicals, and then they show that at a male producing temperature, all the eggs turn out to be female. People are still using that argument today in court cases, that shows incontrovertible proof of no thresholds. But in 2007, we did a comprehensive review of all the data, and there was a serious flaw. Out of something like 44 studies, only a handful of studies, ours and a couple of others, actually measured whether the chemical got inside the egg. You can't even verify that the chemical gets inside the egg. We tried for 3 years. You can't figure out how to get the chemical inside the egg successfully. And the other people who had bothered to measure it found the same thing we did. But everyone was just assuming that the effect they got was due to the chemical getting inside the egg. Again, we have to just look at what the underlying theory is. Does it actually explain all of the data? Are we considering the things that are inconsistent with the data as well as the things that we can say are? And does it make a lot of sense? And I've come to the conclusion that this is not one of our big public health issues. It's not something that I think we're spending too much time and too much money on it. I think we would do a lot better if we were more focused on trying to ensure that we can unequivocally define the conditions under which we can safely use chemicals, and pay a lot less attention to these effects that we can sensationalize and that we can basically tell a story that is one of doom and gloom. If we find something that's real, absolutely, we need to act on it. But I think we would do better trying to focus more of our attention on making absolutely sure we can define the safe levels. And if we can't define a safe level, fair enough, don't use the chemical.
There is a lot there. Like, what's the potential downside of this sensationalism or over attention on some of this stuff? Maybe a diverting of attention to maybe more worthy and impactful research that is more likely to generate outcomes that we're looking for from the research. I don't know. This is really interesting to me. I've been thinking about it a lot lately. So just for context, I am currently a PhD candidate, and I'm interested in the impact of misinformation on environmental outcomes. And something that I've just continuously come up on is sustainability is very complicated. And so what often wins is simplicity. But considering the reality of things, simplicity is often incorrect. And therefore, the popular motif is usually wrong. Like, most of the things out there about environmental impact for products is just not right, even at like technical conferences. There's just people who talk very simply that just constantly get a platform, and it's very frustrating. I was thinking about that. I was also thinking about this in the context of conversations about doubt mongering. Sowing doubt was a historical practice of certain sectors to delay policy oversight. And no doubt the tobacco industry was a really good example of that. in conversations in academia for people who research this space, I've also heard people paint, like, for example, the plastics industry or people from the plastic sector as it's the same. They just assume because it's the simple, from my perspective, it's the simple narrative that, well, plastics equal bad. It's all over the social media. It's all over the media. Therefore, that's what it is. And it's so complicated. It's just really, really hard to separate fact from fiction. And you have to, if you want to productively move forward on so many of these different topics, you have to understand what's going on, but it's just getting harder and harder. Like, science is increasingly inaccessible, even to scientists. You have to increasingly be a specialist. There's a real need for science communication, but it's underfunded in academia and in industry. It's something that I'm faced with, and I know, like, so many other science communicators are faced with the same thing. This also reminds me of a theory that was put forth in conservation research. I actually had the lead author on my podcast a few years ago, Adam Ford from the University of Alberta, I think. And he coined this term, misplaced conservation, to think about this in the context of conservation, where, like, misinformation gets in the way of getting to the right outcomes. And so he gave quite a few examples in the paper that he published. For example, there was a population that was trying to save the monarch butterflies. And so they went and planted a bunch of milkweed, but unfortunately they planted the wrong milkweed. It actually made the issue worse. A take home from the paper that I thought was really fitting here as well is that outcomes are ultimately the arbitrators of conservation or whatever success. Good intentions do not excuse easily foreseen harm. And, like, misinformation is hard to tease out intention, so that's really challenging. But I feel like a lot of people feel like the things that they're saying is right because they feel like they're morally righteous, and people see that these people, or feel that these people, are morally righteous. So how could they be wrong? This is beyond the scope of this conversation, but certainly things that I've been thinking about a lot lately. I'll get to a question that I think comes up nicely after some of the things we were previously talking about, which is, what are the pharmacological principles that should guide thinking and research on endocrine disruptors, and why are they so important? Also, if you want to comment on anything that I just said, by all means.
I will, but I'll try to make it brief because you said a lot of really interesting things. Years ago, and I can't remember how many years ago, I heard about a talk given at the American Chemical Society meetings. I was giving a talk in a different session and I missed it, but I heard such good things about it. I contacted people who gave the talk and invited them to speak to a group that I'm involved with, which is the Endocrine Policy Forum. And our website is endocrinepolicy.org. There's a lot of information there about endocrine disruption. It's presenting, the contrarian view, some of the things I've talked about today, and I'll get to the pharmacological principles in just a second. But these individuals' names were Jay Byrne, and he publishes now, or has for a long time published it's an online document called Bonus Eventus, and the other individual was Josh Gilder. These two people were very interesting. Gilder was a speechwriter for, if I'm remembering correctly, Reagan and Bush 41, our presidents. And Jay Byrne was an oppositions researcher for the Clinton campaign. So two people who come at politics, and they weren't scientists, but they were, coming at things from opposite sides of the aisle, obviously. But they worked together very well, and they pointed out that if you want to understand what's going on, you have to understand that humans are storytelling beings, and that this is not my area, so I'm just trying to capture the concept. He says you have to understand that humans learn best through stories, and these stories have three elements. There's a villain, a victim, and a hero. And they recounted ancient stories, and you can think about all kinds of ancient literature has a lot of those elements. That's how we learn. And he says that's what sensationalism today is doing. There's always that narrative. There's the villain, the victim, and the hero. The hero always assumes maybe they truly believe that they have the solution or that they have the moral superiority. But that's a very simple narrative that, as you point out, is often wrong. So I just wanted to mention that this is interesting. They also pointed out that this was years ago that I can't recall the term that they used, but the global fear industry is the way I would term it. And they're adding anti-vaccines, anti-chemicals, anti-pesticides, all of it together. Was at that time, it just knocked my socks off. Nearly $1 trillion a year industry. Throw up your hands and say, gee, everyone's horribly conflicted. How are we going to get to the truth? And that was your theme, and I couldn't agree more. But it was interesting. The pharmacological principles we should keep in mind. These go back to the early 1900s. Their potency, which potency applies to more than just hormone receptors. It has two components: affinity. I mentioned the lock and key model. So this applies to any small molecule in the body, whether it's a hormone or any other molecule that's, say, metabolized by an enzyme. There's an affinity between those molecules. So a hormone has affinity for its receptor. That means how tightly those two molecules interact. The receptor is a very large molecule. The hormone is a small molecule. An endocrine disrupting chemical is a small molecule. So potency is a term I've mentioned. Well, that has two components: affinity, and then something we can't quite measure directly, but it's called intrinsic efficacy. So if a hormone activates a receptor, that's a product of how tightly it binds, how securely it binds to the receptor. That will determine its occupancy, how many receptors it occupies, because if it binds tightly, it's going to be there more of the time than a chemical that binds much less tightly, that has lower affinity. And it will be a strong activator of the receptor if it has high intrinsic efficacy. If it binds tightly and has no efficacy, then it's an antagonist, and hormone antagonists are also used as drugs. So potency is a very well-established pharmacological principle, and it obeys also what we call the laws of mass action. So when I described Lyle and I's most recent paper on potency, it's kind of one in a long stream of papers I've published on the issue of potency. We used calculations based on the laws of mass action. And the other principle is kinetics. And you've alluded to this. Kinetics involves, we can think of pharmacology and toxicology in two realms. There's pharmacodynamics, which is the way the chemical affects the body. And then there's pharmacokinetics. And then the terms toxicodynamics and toxicokinetics are the same thing, but in the realm of toxicology. So kinetics is the effect of the body on the chemical, because when we're exposed to a chemical, we can absorb it or not absorb it. Once it's in our body, it distributes throughout the body. Certain organs in the body will metabolize, or another term you'll hear is biotransformation. They'll convert the chemical to something that's usually more water soluble and easily excreted. So we break it down and we get rid of it. And that process happens with our foods, even with our own hormones. So potency and kinetics, you really have to understand those kinetics, because if you can never get enough of the chemical to the site where it would have some activity, it's not going to ever have that activity. It's just not possible. So that's a big player in this endocrine disruption question. Pharmacokinetics or the toxicokinetics, we just call it kinetics. So the dynamics and the kinetics, the potency particularly, and the kinetics are key. Those are the foundations. And if you're not paying attention to those and thinking about the results of research in terms of those basic principles, you're going to miss things, and you're going to make interpretations that simply don't make good sense. And there's been too much of that in the endocrine disruptor arena, in my view. So those I think are important. So when you're talking about ingredients in products, ask those questions. Is it potent? Is it really a potent endocrine active chemical? And what are the kinetics? How much actually gets into my body? Or is it only an effect on the skin that you're worried about? But if you're talking about reproductive effects, you're talking about effects on reproductive organs. So that chemical has to get through the skin and then distributed throughout the body. You have to get enough of it that it overcomes your metabolism, and then it's potent enough at the endocrine organs that it actually causes an effect. And those are the basic principles I would very much like to see take a higher prominence in the issue of endocrine disruption. Those issues have been given short shrift.
Right now, a big conversation in beauty and beyond is with respect to validating safety, especially when we're talking about different contentious ingredients like UV filters. There's a whole mess with getting the organic filters on the GRAS list of approved filters. Part of the hesitation or limitation right there is in the use of animal testing to validate safety.
Yes.
In light of the shortcomings at the moment of alternative testing methods. It's a big conversation. So much work is being done into advancing non-animal safety testing methods. I've had several podcasts about this already, and presentations at previous summits, but it is something that the cosmetics industry is talking about. So this brings me to a comment that I had on my podcast when I did it with Lyle, and it'd be interesting to have your point of view. So this is from Me She D. I thought it was a really good comment that kind of speaks to some of this. So the comment was, I'm listening to the podcast now, and I've come to a shocking realization that people who promote misinformation and fear-mongering of safe and effective ingredients in cosmetics are the cause of animals who may have to suffer in lab studies, so more biased individuals can prove a point that isn't even true. They are so determined for an unrealistic outcome that certain chemicals may be harmful when, in the studies, they use high amounts that would never be used in everyday life on cells and animals that are not the same as humans. Sadly, animals will be studied in the lab for irrelevant or invalid reasons. It's futile, yet these animals suffer anyway because people with no relevant expertise push for its demand. Curious about your thoughts on that comment.
It's a thoughtful comment, and it's one that I have heard many times. And I also want to make sure that I make clear we do need to ensure the safety of chemicals. I'm not at all trying to paint the picture that all chemicals are safe. We don't need to worry about any toxic effects, and any and all concerns are simply fabricated. Particularly in the endocrine disruptor arena, you will see papers that claim to be testing human relevant doses and seeing effects, low doses. So again, all the things that I've talked about still have to be put into place. So you can do experiments at human relevant doses. The reason given for not doing them at human relevant doses is that it's too difficult to see toxicity if it were occurring. You would need too large a number of animals being studied. And that's sort of I don't know what the proper the term for the logical mistake that's being made. I don't know if there is one, but it's assuming that you can increase your statistical power by increasing the dose, or that you can do the same thing by just testing 10 or 100 times as many animals. They're not interchangeable. It's sort of like asking the question, what's the risk of drinking a glass of wine every night with dinner? Gee, we would have to study hundreds of thousands of people because the effect may be very small and only discernible in a few people. So we'd have to study this huge number. Instead, we'll just have 100 guys drink a bottle of whiskey every night and see what happens. And that's kind of what we do with animal studies. We just give these high doses so that we can see something, and then we assume that it has some relevance for lower doses. That's problematic. I want to make sure that we do give the good credence to the need for safety testing chemicals. And the issue of animal testing is an ethical one, it's an emotional one, it's a very legitimate question. Unfortunately, we are not yet at the stage of knowledge, in my view, where we can reassemble the animal from all the component parts. I consider myself a mechanistic pharmacologist. I'm not a clinical pharmacologist. I don't have an MD. I'm not evaluating patients. I've been involved in the very basics side of it, and then got into toxicology after my postdoc. So it's basically the flip side of the same coin, looking at mechanisms. So I'm all in favor of these in vitro studies and what's been called new assessment methods. But as a quick aside, I find that a meaningless phrase. What's new is just everything that's not old, or vice versa. So what does that mean? It's kind of a term that means in vitro and in silico, computational types of methods. I'm completely in favor of those, and I think that that's ultimately the best way to go, because it would rely on first principles and the very basics of how things work, but we're not even close to being there. So unfortunately, I don't see a credible end to all animal testing right now. I wish I did. However, one of the things that I made a mention a while ago about focusing more on defining the conditions under which we can use chemicals safely. I think that would be, when we have to use animals, I think that would be a far more ethical way to do it, rather than, like the space shuttle. Shall we test automobiles by dropping them back into the atmosphere? They're all going to catch on fire, and then that doesn't make any sense. We're doing the same kind of things in toxicology. Let's dispense with the ridiculous and absurd high dose testing. Let's focus on we can do that with in vitro studies. That would be fine. We have to keep in mind the potential irrelevance of that. But for animal testing, let's use that only when we need to. And then, this is a paradoxical statement, but sometimes using fewer animals is actually wasteful, because we don't get a clear answer. So what we're doing now is we're testing doses that are irrelevant, and we're trying to minimize animal use by testing only the statistically minimum number of animals we need to potentially show an effect. And I don't think that's getting us to the answers we're seeking. I think we would be better off focusing on the kinetics and a relevant dose range, and then trying to figure that out first. And then when we need to actually do toxicity tests on animals, focus on the meaningful range. And yes, use enough animals that you get a conclusive result that is relevant and applicable. Don't waste animals doing studies that don't really give you the answers that you need. That's the ultimate waste. But I agree with the question that I think ultimately I'd love to see no animals used in experimental research. Unfortunately, I don't think our knowledge base is there yet, but it's getting better.
I think the question also is getting at not necessarily I think there's understanding that there is a need at this current moment for animal testing, but the sensationalism of this topic has driven maybe some unnecessary testing. I think that was where they were kind of coming from.
Yes, and I understood that. I didn't mean to imply that the questioner had the bias that we should immediately.
I know a lot of people do, though.
A lot of people do, and I'm just saying that
especially.
I think as a goal, that's a laudable one. I'm on board with that, and I didn't mean to imply that the questioner thought that, but it does raise the issue of all this research that is not toward falsification of a theory. It's done according to our incentive status. If you want to be funded, you continue to do these studies. And I review so many studies that really show nothing. They use a lot of animals. Often they don't use enough animals to really make the point that they're making or that they're trying to make, but they have enough to give a suggestion or a statistically significant response. It's not a very compelling result. The magnitude of the responses, how severe the effect or how great the effect, is marginal. And I can look at the whole study and say, gee, what a waste of time and effort. But it got a publication. It reported something that hadn't been reported before and can go back into a grant application. And that's our incentive structure. If you want to build a successful research career, you have to have publications and you have to have grants.
So this is a ginormous topic that we're just brushing the surface with. But we've been now talking for close to 2 hours. So I feel like it's probably a good time to wrap up. And so I'll ask the final question I always ask all my guests, which I think gives a lot of room if I miss something that you want to say to my audience. So the question is, do you have any final take-homes that you'd like to leave with my audience, and or are there any messages that you would like to get out there that we haven't had a chance to cover?
The message is be skeptical. I don't mean mistrust motives and things like that. I can't get into that, where I think people are so horribly conflicted, I'm more conflicted than I could possibly imagine, so science gives us hopefully a way to try to be a little more objective and measured about that, but it requires some skepticism. It requires saying, okay, let me stand back from that. Let me consider it seriously. Does it make sense in total? If I were to summarize, I think that's one of the things for incentive structure, all kinds of reasons that I see often missing in the discussion. It's not about sowing doubt. It's not about manufacturing doubt. It's about trying to get to one can call it truth, at least trying to get to an accurate answer.
Thanks again to Chris for coming on the podcast to share your expertise with us. I hope you learned a lot and enjoyed the conversation as much as I did. Quick reminder, if you're not already subscribed to the podcast, please do. And if you haven't already, please give the podcast a review. If you enjoyed this episode, please share. And if it's accessible, you can also support the podcast on Patreon at patreon.com/theecol. Thank you again to all my Patreon supporters who have supported my SciComm efforts over the years. That's all for this week. Thanks for tuning in.